Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back, folks. In this video, we're going to look at example E3.2. It's entitled The Use of MDMT Exemption Curves with Stress Reduction. And this is with regards to ASME Section 8 Division 2. And this is a direct example with a few comments from myself from ASME PTB-3, the 2003 version. So all the MDMT examples are part of part 3 of Section 8 Division 2, which falls under materials. Okay, so let's take a look at this example we have here. We're doing a division 2 analysis. We have the same, this is exactly the same example as before so that you can see the progression. But so we basically, in summary, it's a post 1999, it's a 516 grade 70 material. It's in the same location as previous. It's the shell to head joint, which is, a category A type of a joint. And so this, we have the thickness is shown here and the corrosion allowance. And, we're using a type 1 type well with a backing strip. And inspection is 100% RT. Okay, so this is what the plan is. There's going to be post-weld heat treatment, like once again, because of the thickness. The MDMT required is -20. Because of all these factors shown here, and if going through the procedures in 4.24, you can get the joint efficiency factor of 1.0. So I've shown a different color here in orange so that you can see how this is different now. So we need more variables to do stress reduction factor. Before, you didn't need as much information just about how the material is processed, for example, the post-weld heat treatment and the thicknesses. But now we need to know the design temperature, we need to know the pressure, we need to know we're going to use the diameter of the vessel, and we're going to need the allowable stresses and the yield stresses at ambient temperature and so on, because we got to calculate our stress. And this is just like Section 8 Division 1, where we need to know how much to extent the part is stressed. So let's look at step 3, the exemption curves. So we're going to refer to figure 3.8 or table 315 for the tabulated version, because we chose that because it's a post-weld heat treated part, so the stresses are lower, and it's a non-welded part. So when we did the example last time, we drew our curves and we found, based upon the governing thickness, 46 millimeters, that we are at -28 degrees centigrade. And of course, we based that upon the curve D, which is the material curve for 516 grade 70D. Section 8 Division 2, the 2019 version, the materials except bolting is found in Annex A3. It's sort of a roadmap of where you need to go. And so for Class 1 designs, we would go to Section 2, Part D, Subpart 1, Table 2A. And then for Class 2 designs, we would go to Table 5A. So let's take a look at Table 2A. And in this case, we're looking for a Section 8 Division 2 Class 1 design. And we basically looked up the material from the previous pages on line 38, and we get the minimum yield strength of 260 megapascals. To continue with Table 2A, you would look for the design allowable stresses from this table, and it's also called a design stress intensity values. And there's a preamble in the appendices that will explain that there's a slight difference because you can add correction factors for your different cases. But in this case, the allowable stress is the design intensity values. Let's take a look at Division 2, the Class 2 materials, and we get 154 from Table 5A. So the allowable stresses is 154 megapascal. So it's the same for Class 1, for Class 2 materials. So let's look at Step 4. Stress ratio, which is equation 3.1, and it's based on the thickness basis. As if you saw the earlier videos, we talked about the different kinds of stress ratios that you could use. But in this example, we're going to be using the thickness basis equations. So that means we're going to have to calculate the actual stress in the membrane of the vessel that we're examining. So we're going to take the ratio on the top of this is shown is the stress that how much the part's stressed, and this is over the available or the nominal, well, basically the available minus the corrosion allowance. Next thing we'll do is we'll continue. We'll calculate the required thickness. So for a cylindrical shell, we'll use part 433, equation 431, which is shown here. And we're going to calculate the corroded diameter, and it's important to do that. So you're looking at the end of life assessment. So, you take the diameter times 2 times the corrosion allowance, and then you get the corroded diameter D. Next thing we do is we put that together into the equation, and basically we solve it for when we get 30.6 millimeters or 1.203 inches for TR. So we'll continue on with step 4. We're going to go back to equation 3.1, which is the ratio. So we've calculated the required thickness on the top, and we got to calculate this, which we'll talk about in a quick second here. And we know our nominal thickness for materials. So for example, a 20-inch pipe will have a standard weight pipe will have a nominal thickness of 0.375 inches, and so that's what what you have available. So in our case, we have how we calculate E is we take we determine E from the tables at the beginning of this video, and we look at the how much inspection's been done and the configuration, but we never allow the E factor to go below 0.8, and that's the same as what is done for Division 1. So we're going to continue to calculate the value, and we put all of the variables together. Our efficiency is 1.0 for our joint. We just calculated the TR thickness, and we know the thickness of the materials, 46 millimeters. Subtract the corrosion allowance, we get a ratio of 0.71. So the part's, fairly well stressed. It's 71% of the it's 71% stressed, so there is a little bit of room to derate or to lower the MDMT, which we'll do in the next step. So we continue on to determine the final MDMT. So we go to figure 313, or the metric version 313 M, or table 317, and I think there's a table 317M as well. And so in this case, we're looking at parts that are, subject to post-weld heat treatment. We're examining non-welded parts in this example. So we'll continue here. So we've got it. Our RTS is greater than 0.25. So, and our yield stress is less than 260 megapascals, or 50 KSI. This is what we'll have to work with. So let's start. And of course, we have post-weld heat treating. We have non-welded parts. So we have a ratio. Our ratio that we calculated last slide was 0.71. We go across, and we use the values of for less than 345 megapascals. We go across and down, and then we finally end up with our temperature reduction of 15.8 degrees centigrade. So we continue on. So we'll determine the final MDMT. So we just take the minus 28.3 that we calculated, and basically in the last video, and a little bit of a summary in the beginning of this video, and then we take the 15.8 that we just did, and and lo and behold, we've got our MDMT down to minus 44.1 degrees centigrade. So this was a very effective way of reducing our MDMT so that we wouldn't have to do impact testing in accordance with Section 8 Division 2. So everything's acceptable, no impact testing. And basically that's all we did. It was we used the MDMT from step 3, and we subtracted the TR ratio. That's all there is to it. So then determine the final MDMT. So let's compare Division 1 and 2. So when we do a Division 2 calculation, recall in the last slide we got minus 44.1 degrees centigrade. And if we compare that, the same thing as close as we can get to Division 1, you get 32.7 degrees, minus 32.7 degrees, excuse me. And that's you can see that Division 2 allows you to reduce your MDMT even further. And recall that since the allowable stresses were the same, by coincidence, that's very rare for class 1 and 2. So the MDMTs are the same for class 1 and 2 materials for this particular example.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.